end of the 19th century, there were several experimental phenomena that led to the notion that could not be explained by thinking of light as a wave. Okay? And so these phenomena generally dealt with interaction of light with atoms and molecules. So when you have light interacting with you have light interacting with small particles like atoms and molecules, the behavior of the light could not be explained by thinking of it as a wave. And the solution to that anomaly was to think of light as though it's a stream of particles, behaving like it's colliding with the atom, or it's like as if it's a particle that's colliding with the atom or the molecule or the electron. Okay, so we now say that light has a wave, as a dual nature. In some instances, you can explain its behavior by thinking of it as a wave. In some instances, it's best to think of it as a stream of particles. We now refer to these particles as photons. So we say light has a dual nature. So this phenomenon is known as wave-particle duality. So the term wave-particle duality refers to the fact that light, which we traditionally thought of as a wave, sometimes behave as though it's a stream of particles. Okay? So the energy of each of these photons, each of these particles, turns out, based on these experiments, you can resolve all of these anomalies by thinking of each photon as carrying an energy equal to h times nu, where nu is the frequency of the light. So there's a connection between the wave nature of the light and the particle nature of the light. So light that has a frequency nu we say is made up of photons, and each of those photons carries an energy equal to h nu. Now this h right here, this proportionality constant, is called Planck's constant, in honor of Max Planck, who was the first to propose the idea when he dealt with the black body radiation, which we're going to talk about next time. Okay, so Planck's constant is 6.63 times 10 to the negative 34 joules second. Okay, 6.626. If you have 4 sig figs here, times 10 to the negative 34 joules times second. Basically, what this equation says is the higher the frequency of the radiation, the more energetic the photon. Okay, what's the unit for the energy of the photon? The unit for h is joules per second. The unit for frequency is per second. So seconds and per second cancel out. That will give you the energy in joules. Okay, so you get more energetic photons when your frequency of your radiation is higher. So simple example here. What's the energy of a photon of red light if that particular light has a wavelength of 632 nanometers? How will we solve that? E is h nu. So h is how much? 6.626 times 10 to the negative 34 joules times seconds. And wavelength frequency is, how is frequency related to wavelength? This is wavelength. Lambda times nu is c, so nu is c over lambda. So this is also equal to hc over lambda, right? So what's the value of speed of light? .998 times 10 to the 8 meters per second divided by lambda, which is 632 nanometers. Nano is 10 to the negative 9 meters. Okay, so seconds cancel out, meters cancel out, so that gives you joules. What is that number? You have 6.626 times 10 to the negative 34 joule seconds times 2.998 times 10 to the 8 meters per second divided by 632 times 10 to the negative 9 meters. Oops, 0. Okay, let me change this sensitivity of the zero tolerance for this. Okay, it's 3.14 times 10 to the negative 19 joules. Okay? So that's 3.14